Welcome back, my fellow mathematicians. In this video, we start our lesson introducing eigenvalue theory. Remember that when we're talking about eigenvalues and eigenvectors, we actually have three separate problems. We're going to call those problems 4a, 4b, and 4c. The standard eigenvalue problem, which is the most common, seen in most introductory classes, is given a square n by n matrix, find an vector x and scalars lambda such that a times x equal lambda times x. We said last time that one of the ways we can generalize this is on the right-hand side, instead of the n by n identity matrix, we could generalize that to a matrix B, and then the generalized eigenvalue problem is to find vectors x and lambda such that a times x equals lambda b times x. In this case, the matrices A and B arise from some modeling context and are square. The third type of problem that we'll focus on in eigenvalue theory is something called a quadratic eigenvalue problem. This is usually left for more advanced explorations in linear algebra. For quadratic eigenvalue problems, we have three matrices. Perhaps we call them M, B, and K, all square n by n, arising in some modeling context. And then we want to find vectors x and scalars lambda such that lambda squared mx plus lambda bx plus kx equals 0. We can group those three types of problems together and simply refer to the entire category as eigenvalue problems. Remember, in our lesson introducing eigenvalue problems, we actually constructed a standard eigenvalue problem as a way to model a couple pendula system, two pendula connected together by a simple extension spring. In that situation, we had Newton's second law in matrix form, so mass times acceleration is equal to the negative stiffness matrix times the displacement vectors of each mass. And we saw that we could actually rewrite that as an undamped, unforced, simple harmonic oscillator equation, as seen here. This actually is not a quadratic eigenvalue problem because in our assumption on that problem, we assumed that there was no energy loss. In other words, there was no damping. If we actually included a damping term, that would give b times the first derivative of u, and that would yield a quadratic eigenvalue problem. Let me say that in a different way. When we look at a coupled mass spring chain or a set of coupled oscillators, if we model energy loss, we actually use quadratic eigenvalue problems to do so. However, since this is an introductory class, the point of this is to set a foundation for further study. What we did is we simplified our physical phenomenon by assuming ideal circumstances, no energy loss, and we started with mu double dot equals negative k times the displacement vector. The goal was to find the displacements of each mass at any time in some observation. We made a further simplifying assumption that the masses on each pendulum bob were identical, had the same measurement. That allows us to bring the mass matrix over to the other side via inversion. And then we define M inverse times K as a single matrix A. This is a classic differential equation, and we use the cosine ensemble. In other words, we say, what if we assume that the displacement vector is cosine omega quantity t minus t naught times some real valued 2 by 1 vector v. With a little bit of work, we actually take a look at the left and right hand side of our differential equation with respect to this assumption, and we get something like the second derivative of u is going to be omega squared cosine omega t minus t naught times v. On the right-hand side, we have negative cosine of whatever's on the inside times a times v. And then we did some algebraic manipulations to show that the only way these two things are true is if the vector v, non-zero, has the property that when we multiply a times v, we get omega squared times v. Introducing notation lambda equals to omega squared, this is actually a standard eigenvalue problem. A times v is equal to lambda times v. Those are the same equations, just with some auxiliary variable called an eigenvalue, which means we've translated the derivative problem, the differential problem of solving this differential equation, which involves continuous functions, into an algebraic problem involving the matrix A. In other words, we have this n by n matrix, and the goal is to find vectors v and scalars lambda such that A times V is equal to lambda times V. This equation does not involve derivatives. It involves analysis of algebraic properties of the matrix A. The question we're going to ask ourselves in this video is, if we know the individual entries of the matrix A, can we use our knowledge of linear algebra to figure out which non-zero vectors send A times V to a scalar multiple of that original V? And can we also determine the scalars that satisfy that equation? Well, in the case of our modeling problem, we know that the matrix A is going to be the mass matrix inverse times the stiffness matrix, and that has these individual scalar values. Each of these is a constant that is observed from our McCusker apparatus. G is the acceleration due to gravity. L is a measurable length of the chord of each pendulum. K is the stiffness of the spring, which can be gotten from a least squares problem. M is the mass on each bob that can be measured using a spring. So we've created a matrix where we know the individual entries. The question is, can we study the algebraic properties to produce these vectors? Let's put that in a different way. We're thinking about each eigenvector v and each eigenvalue lambda as showing up in pairs, meaning that when I multiply A times V, I'm going to get a scalar multiple times V out. The scalar multiple is called the eigenvalue. The vector itself is called the eigenvector. We want to find those in tandem. And the question is, if we know the entry by entry definition, can we produce that information? This is where our knowledge of the rules of algebra comes into play. If we look at that original equation, AV times lambda V, we can actually get the right-hand side equal to 0 by simple vector subtraction. Let's bring the entire right-hand side over to the other side. And then notice that in between the scalar lambda and the vector v, we can always multiply a vector by the identity matrix and not change the value of the equation. Now we have AV minus lambda I2 times V. This is a 2 by 1 vector. That's a 2 by 2 matrix. That works out all right. Notice that both terms have a factor of vector V on the right-hand side. We can actually bring that vector out. So now we're looking for a non-zero vector V such that we multiply that non-zero vector V by the matrix A minus unknown scalar lambda times I2. That non-zero vector sends this matrix to 0. That's the 0 vector. But let's refer back to our knowledge of linear algebraic theory. When does a non-zero vector send a matrix to 0? What is the property of a matrix such that it has a non-zero set of scalars that when combined with the columns send that matrix to 0? We know something about that based on our study of non-singularity. We can find a non-zero vector v that sends A minus lambda I2 to 0 if and only if the matrix A minus lambda I2 is singular. In other words, it has linearly dependent columns. We know by our study of determinant that matrix is singular if and only if the determinant of that matrix is equal to 0. But we actually know the values of the entries of A. We know the values of the entries of I2. We're looking for scalars. The determinant turns this matrix expression into a corresponding scalar expression. So this condition that we're looking for values of lambda such that the determinant of this matrix is 0 allows us to express the problem of finding eigenvalues as a scalar equation, as an algebraic equation. Later in this lesson, we're going to formally define this equation when we're looking at an n by n matrix. Take the determinant of A minus lambda in and set that equal to 0. That is an algebraic equation involving the variable lambda. We're going to call that the characteristic equation, and it's used to find eigenvalues. Before we introduce all that formal terminology, let's take a look at what this means for our specific coupled pendula problem. When we look at the matrix A minus lambda I2, lambda is an unknown. We're searching for those values that satisfy our eigenvalue equation. We know the entry by entry definition of A, that's given here, and we know that lambda times I2 is a diagonal matrix with unknown scalar lambda on each diagonal element. When we subtract those, we get this 2 by 2 matrix where the diagonal coefficients of A have a term of negative lambda. We're subtracting lambda from each of the diagonal coefficients, and the non-diagonal elements remain unchanged. But remember, when we're looking for our eigenvalue eigenvector pair, the eigenvalues must satisfy what we call the characteristic equation. Lambda is an eigenvalue of this matrix if and only if the determinant of that matrix is 0. In other words, that matrix is singular. Well, we know how to take the determinant of a 2 by 2 matrix. We take entry 1, 1, multiply by entry 2, 2, and then subtract the product entry 2, 1, multiplied by entry 1, 2. In this case, we see G over L plus K over M minus lambda squared. There's 2 of those. And then we're going to subtract negative K over M times negative K over M, or in other words, we're going to subtract negative K over M squared. 2 things to notice immediately. First, the negative inside the square disappears because negative 1 times negative 1 is positive. And then the second, this is a polynomial in terms of lambda. It's an algebraic equation where if we were to expand this, it's a quadratic polynomial. So it's going to be like some factor times lambda squared plus some coefficient times lambda plus some constant. That polynomial is called the characteristic polynomial of our matrix A, and it's used to find the eigenvalues of that matrix. Notice the characteristic equation is to find the roots of this polynomial. So we are literally trying to find where is this quadratic polynomial equal to 0. That's a classic problem in mathematics. That's an algebra problem of finding roots. Given that I know that this matrix is non-singular if and only if this polynomial is equal to 0, I can bring the right-hand term over to the other side in this case. I don't actually have to expand the polynomial. And I get that this determinant is equal to 0 if and only if the quantity G over L plus K over M minus lambda squared is equal to K over M squared. Taking the square root of both sides, I can actually say something. We know that both K and M are positive constants. When I square a positive, it stays positive. When I take the square root, we also get a positive. So no need to track extra information. That square and the square root disappears. Over on the left-hand side, when I take the square root of a square, we are not yet sure what the value of lambda is. That might be positive or negative. The square root of a square in that situation we say is the absolute value. So now we're searching for lambda such that the absolute value of G over L plus K over M minus lambda is equal to K over M. Because this is an absolute value, we can also factor out a negative with no cost. The absolute value of negative 1 is 1. We can reverse this, and then we're trying to solve this algebraic equation. Remember that an absolute value is equal to a positive number if and only if the argument of the absolute value, the thing on the inside, is equal to the positive or negative of the number on the right-hand side. So we want to find lambda such that lambda minus G over L plus K over M in parentheses is equal to the positive or negative of K over M. We note that there are actually 2 distinct solutions to that algebraic equation. 2 separate eigenvalues. Let's take a look at eigenvalue 1, which we're going to say is the first natural frequency. Specifically, let's solve for this equation when we set the right-hand side equal to a negative. In that situation, we say that lambda 1, we're going to bring this term over to the other side via addition. So lambda 1 is G over L plus K over M minus K over M. The K over M's disappear, and I'm left that the first eigenvalue of the system is G over L. Remember, in this application, the eigenvalue lambda 1 was actually a natural frequency omega 1 squared, which means that omega 1, the thing inside the cosine, is going to be the square root of G over L. Guess what? That's the same frequency of a simple pendulum with no connections. In other words, in the first eigenmode, the frequency of oscillation is as if each mass is a simple pendulum with no connectivity. It is the natural frequency of those pendulums in isolation. To find the second eigenvalue, we're going to set the right-hand side to a positive. In that situation, we're going to say the second eigenvalue, or what we call the second natural frequency of our system, lambda 2, we're going to bring this term over to the right-hand side via addition. So lambda 2 is G over L plus K over M plus K over M. In that case, we have 2 values of K over M. So lambda 2 is going to be G over L plus 2 k over m. Remember though that the eigenvalues were the squares of the frequency of the cosine under the cosine ansatz or the sine ansatz. It didn't even matter. So in this case we say omega 2 squared is g over l plus 2 k over m, which means that another frequency of cosine that might be used is omega 2 equals the square root of g over l plus 2 k over m. Remember, the goal is to find not only scalars lambda, but also corresponding vectors v, such that a times v is equal to lambda times v. In this case, we have two distinct eigenvalues, lambda 1 and lambda 2. We can use each of those separately to find the corresponding eigenvectors. Let's start with the first natural frequency, the first eigenvector. In this situation, in the first eigenvector, we say that the scalar lambda 1 is g over L. The question that we have is, can we find a non-zero vector v1 such that a times v1 is lambda 1 times v1? But as we saw before, the only way that a times v1 is equal to lambda 1 times v1 is if the matrix A times lambda 1 times I2, that's a scalar, that's a 2 by 2 matrix, multiplied by the non-zero vector V is equal to 0. We actually have the entry by entry definition of that matrix. It's going to be the matrix A where the diagonal elements are shifted down by lambda 1. Lambda 1 was g over L, so I take the diagonal elements of A and I subtract g over L, and then I want to find from this matrix, can I multiply by the vector v1 such that that matrix times v1 is equal to 0. Notice that when we subtract g over L, those terms disappear, and my matrix A minus lambda 1 I2 is literally k over m, negative k over m, negative k over m, k over m. Now the question is, how do I take linear combinations of these columns and send that equal to the 0 vector? But column 1 is the negative of column 2. Another way to say that is if I added column 1 to column 2, I get 0. Another way to say that is the first eigenvector associated with eigenvalue 1 of g over L is going to be 1, 1. In other words, when I multiply this matrix by 1, 1, I get 0. Which means for my modeling matrix A, I know that A times V1 is lambda 1 times V1, where lambda 1 is g over L and V1 is 1, 1. That is an eigenvalue eigenvector pair. This corresponded to a natural frequency of the square root of g over L in our actual system, which has an interpretation which we'll get to in just a minute. Of course, in this system, we don't just have one eigenvalue, we have two distinct eigenvalues. In fact, the second eigenvalue is g over L plus 2k divided by m. The question is, can we find a vector v2 that is non-zero and satisfies the equation a times v2 is equal to lambda 2 times v2. We can isolate the right-hand side and set it equal to 0. We'll bring this entire term over to the left. So I have the matrix A minus lambda 2 times I2. We want to send that matrix to 0 with a non-zero vector. We can actually write that matrix out specifically entry by entry by recognizing we know the values of A, and then we also know that lambda 2 I2, that downward shift, is going to subtract on the diagonals that value of lambda 2. Notice that when we do that calculation, the g over L plus k over m, g over L disappears, one copy of k over m disappears, and that shifts this entire diagonal entry, both of them, to the negative value. So this is negative k over m in column 1, and then I have negative k over m in column 2. And the question is, how do I take linear combinations of those columns and send it to the 0 vector? But in this situation, we see that column 1 is identical to column 2. Another way to say that is if I take one copy of column 1 and subtract a copy of column 2, I indeed get to 0, which says that my second eigenvector associated with eigenvalue 2 can be 1, negative 1. But this implies that we found the second eigenvalue eigenvector pair where A times V2 is equal to lambda 2 times V2, where lambda 2 is g over L plus 2k over m, and V2 is 1, negative 1. Remember that came from assuming the cosine ansatz, where the angular frequency of cosine had the relation omega 2 squared is equal to lambda 2, which means that the second type of angular frequency that produces a pure cosine oscillation of each pendulum is going to be the square root of g over L plus k over m. Let's go ahead and interpret what this means in terms of the dynamics of our system. When we look at the eigenvalue G over L and we look at the vector V1 equals 1, 1, what that tells us is we actually can infer information about pendulum dynamics from that eigenvalue eigenvector pair. Specifically here we have this simulation of pendulum motion. Notice in the simulation I actually have control of the spring constant, I have control of mass 1 and mass 2, and I also have control of the initial position for both the left and right masses. In this case, we're starting with the assumption that both the left and right masses have zero initial displacement, and that's why the solution to this differential equation is trivial. The masses don't move at all. The solution is the zero function. However, when I move mass 1 towards mass 2, when I push the left mass towards the right mass, we see this seemingly quasi-periodic function that does not look like a pure cosine. The point of the eigenvector 1, 1 is to say, if I displace my original left mass and I displace my right mass the exact amount, check this out. When that happens, this system is going to produce an identical cosine. It's going to be the natural frequency of a pendulum with seemingly no effect of the spring constant. And in fact, as I move the spring constant, it actually doesn't matter how stiff the spring constant is. The eigenvalue itself has no factor of k that shows up. The only thing that matters is the value of G over L. Now, sadly, in this simulation, I did not allow us to control L. I wish I did. In this case, check it out. The omega 1, the frequency of cosine, tells me that the angular frequency is going to be G over L. Another way to say that is if I looked at the amount of time that it takes the mass to travel one full cycle, so here we go, goes all the way up, that is now what we call half a period, and then it goes all the way back down. Once it hits that little apex, we can actually kind of pause it right there. That's going to be a full cycle. We can measure that cycle in seconds. We'll call that capital T. The angular frequency is going to be 2 pi divided by capital T, and that is only a function of G over L. On the other hand, when I look at eigenvector and eigenvalue 2, eigenvector 2, 1, negative 1, says, hey, if I displace my left mass towards my right mass, the amount that I displace it towards my left, I should do the negative in my right, and if I do that, I'm going to get a pure cosine term out. The angular frequency of that cosine is going to be the square root of that eigenvector. In fact, if I were to lessen the spring constant, the angular frequency decreases because the inside of the square root is smaller. When I take the square root of a smaller number, I get a smaller number. I can do the same effect with the mass m. If I decrease mass m, notice that they have to be the same for the cosine thing to work out in a pure way. The bigger m is, that means the smaller this ratio is, and that means the smaller the square root. When I make m smaller, that angular frequency increases. So if I want to make the period of oscillation larger, I increase m. If I want to make the period of oscillation smaller, I decrease m, or I increase k. That's what that's telling me. And what this means is that the values of the eigenvector tells me how to put my system into the natural frequency of a pendulum. In other words, how do I get pure cosines out of that motion? One way to do it is the amount that I displace my left mass, displace my right mass in the same position. That's eigenvector 1, 1. In that case, we get a pure cosine and they match each other. They're kind of symmetric. In the other way to do it, the amount that I displace my left mass, I displace my right mass in the exact opposite direction. That's where I get 1, negative 1. And I get cosines, but the spring constant now comes into effect. The fact that there's a 2 in the numerator means that the spring gets extended twice that amount for the same motion because the left and the right mass are displacing in the exact opposite direction with respect to each other at the exact same time. Not only do the eigenvalues and eigenvectors of this matrix tell us about what we call the natural frequencies, but pretend that I put my system into non-periodic or quasi-periodic motion. The claim is that these solutions are actually going to be linear combinations of the two eigenstates. Specifically, if I know eigenvector 1, 1, an eigenvector 1, negative 1, and the corresponding eigenvalues, I can actually get a precise description of this exact function by taking linear combinations of that information. Isn't that just jaw-dropping? We solve complex differential equations to be able to predict the exact location of the center of masses using algebraic problems. This is the benefit of eigenvalue theory. The last thing I want to introduce in our introduction to the theory is this concept of what we'll later know as diagonalization. We'll have to wait 2 lessons to actually get there, but remember that each eigenvalue and eigenvector pair, we can group those together as a matrix. So in the first column, imagine we have A times V1. In the second column, we have A times V2. Those are both 2 by 1 vectors. Over here, A times V1 was lambda 1 times V1. A times V2 was lambda 2 times V2. On the left-hand side, I can factor out an A, and I get A times the matrix V1, V2. Those are both columns. Eigenvector 1, 1, eigenvector 1, negative 1. On the right-hand side, if I take linear combinations of those columns, notice lambda 1 times the first vector, 0 times the second vector gives me column 1. 0 times the first vector, lambda 1 times the second vector gives me lambda 2 times V2. That allows me to write the eigenvalue information in matrix form. This is later going to be known as a matrix factorization. Do you see the theme? In fact, A times the matrix V, where the columns of the matrix V are the eigenvectors of the matrix A, is going to be that same matrix V times a diagonal matrix lambda, where the main diagonal elements of that matrix are the eigenvalues. Now, one of the questions that we're going to ask is, when can we do this? What type of matrices allow us to find the number of eigenvectors is equal to the number of columns? What type of eigenvalues show up in matrices? How do we find those? How do we calculate them? Does the theory of eigenvalues give us insights into other types of problems? Those are the exact type of questions that we're going to ask as we introduce eigenvalue theory. In the case of our specific ordinary differential equation problem, this matrix equation has this entry by entry form, and we will see the fact that this matrix is symmetric tells us a lot about the eigenvalues and eigenvectors. It is not a coincidence that this symmetric matrix has real eigenvalues and orthogonal eigenvectors. That's a theorem. It will take us 3 lessons to build that theorem as a team. Now that we've seen how powerful eigenvalues and eigenvectors can be for analyzing complex phenomenon, including vibrations, electrical problems, etc., 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 we are going to start to build our intuition about eigenvalue theory. That's the remainder of the lessons in this introductory course.